Welcome, everybody. Thank you for joining us today for this session of our HACC Tech Talks series. I'm Andrew Schmidt, and I'm the host today. I work for the AMD University program, and again, we're excited to have two great talks. Briefly, for those of you who may not be familiar with the HACC program, the Heterogeneous Accelerated Compute Cluster is a special initiative from AMD to support novel research in adaptive computing acceleration for high-performance computing and AI applications. HACC centers have been set up at our partner universities around the world, and each HACC site has compute nodes that integrate AMD EPYC processors, AMD Instinct GPU accelerators, AMD Alveo accelerator cards, and AMD Versal adaptive SoC accelerator cards. Members of the program can use these resources to carry out their own research, and the HACC Tech Talks series is intended to highlight the application and research related to these hacks. So if you're interested in the program or any of the previous Tech Talks, you can find out more information here. There's a link at the bottom of the screen and also on how to apply and get involved. So we definitely encourage you if you're at all interested. Today we have two great talks. They're about 30 minutes each. The topic is kind of a broad on HPC applications, FPGAs, some software tools and experiences, and then also SmartNIC. We're going to start with our first talk, which is StreamFlex, harnessing FPGA capabilities at software compile time via virtualization, precompiled hardware binaries. This talk will be given by Gregory, who is a fourth-year PhD student at the University of Illinois Urbana-Champaign, or UIUC. His research focuses on heterogeneous and reconfigurable computing with an emphasis on two key areas. First, understanding the heterogeneity of modern computing systems across both cloud and client environments. And second, lowering the barriers to adopting reconfigurable computing for hardware fabrics such as FPGAs and AI engines.
Hello, everyone. My name's Gregory. As Andrew said, I'm a fourth-year PhD student, and recently I've started working on implementing a project on the V80. And during this process, because the V80s is so new, I went through a lot of struggles to figure out how to get the V80s to work. And after talking to some of our AMD colleagues that's been collaborating us through the HACC program, we realized that it might be very beneficial for the wider HACC community, who also has access to the V80s, to benefit from the findings that we at University of Illinois went through. So the V80s is like a long-awaited FPGA that's built for the cloud. So it's a successor to the previous Avio FPGAs like the U280s, the U55Ts. It's the first accessible data center FPGA that has Gen 5 link speeds, and it also has up to 800 gigabits of network bandwidth. And compared to other Versal data center FPGAs like the VCK 5000s, there is an actual emphasis on the PL rather than a mixture of PL and AIEs. And so with this new capability, we at the university were very excited to experiment and implement various different ideas on this, where you could imagine that previous applications previous research topics such as FPGA acceleration, FPGA virtualization, and FPGA-based NICs would hugely benefit from this capability that the V80 brings to the table. But then the V80 has a certain number of challenges. First of all is it doesn't have a Vitis platform like the previous Avio generation. So a lot of the flows that were previously built around the Vitis platform had to be migrated into the Vivado-based flow. And so that would either entail that you build your design in a monolithic way where you would have a monolithic bitstream, or you would have a specific wrapper around everything where you would just reconfigure the user tile, which isn't implemented and which was our goal. And so if we go through the Vivado flow, if you just go through the Vivado flow and just do the implementation, what would happen is every time you reconfigure the FPGA, because the PCIe endpoint changes, you would have to reboot the system, and that is fundamentally not very compatible with server-based systems where other users are using the server for other use cases like GPUs or other FPGAs. So our goal was to leverage the DFX technology that AMD supports in general, where users of the V80 can just reconfigure just their portion of their application so that the host does not need to reboot after reprogramming. And another goal that we had in mind was not to do DFX over JTAG, but over PCIe. And the reason we wanted to do that is because DFX over PCIe takes milliseconds, while JTAG takes seconds. And also for our systems, because we have a mixture of different FPGAs and GPUs, if we were to have the JTAG cable running inside the machine, it was not very compatible with more production grade systems. So we wanted to get DFX to work so that for larger scale systems, we don't have to connect JTAGs to each FPGA. And so the rest of the talk is organized as follows. It's mostly about my journey on getting DFX over PCIe to work on the V80s. And the flow goes like this, where I first go over AVD, which is the AMD's jumping off point. And then I briefly discuss some details regarding the CPM5 controller of the V80s. And then we discuss what the documentation for them actually mean and try to read between the lines of the document. And then I go through the process that I went through to integrate this with AEVD, the AVD design. Just to give you a brief overview, if you want to work with the V80s, you probably want to start with the AEVD platform. The AEVD platform is provided by AMD to help users get a jump head start on implementing designs for the V80, and it's just a bare minimum Vivado design where users can add their stuff so that they can implement various applications like networks or acceleration, and it's right now, if you download it from AMD, you would just be able to see the device being shown in LSPCI. AVD out of the box has its own drivers, the AVD drivers, but it also works with widely known QDMA drivers that's been maintained by AMD for years and years at this point. And just to go into a little more detail about the V80s, the V80s is part of the Versal family, and the Versal family has something called the CPM5. The CPM5 is a hardened logic block, which acts as an endpoint to the PCIe fabric. And so compared to other Alveo platforms like the U280, the user doesn't actually instantiate a soft QDMA IP which acts as the PCIe endpoint, but there's like a hardened logic block that the user configures to their liking so that the host can see the device. And so after reading the documents regarding CPM5 and also reading some documentation that's on the AVD website, we found that for the AVD design, they went with PCI controller 1 instead of controller 0 because they wanted to be PCI SIG compliant by using the bottom 8 lanes. And just to reiterate what I just said previously, there are two PCI controllers on CPM5, controller 0 and controller 1. And because we're starting with AVD, we started our jumping off point was also with controller 1 as well. And so now our goal was to just implement DFX over PCIe. And based on the document that's available, most mainly PG346, it seemed like just getting DFX to work over PCIe was simple as just writing to the slave boot interface. And there's these certain nomenclatures like tandem and DFX, which are associated with DFX, but based on the documentation, we thought that it wasn't necessary to get tandem to work for DFX. So tandem is this technology that AMD provides, where to meet the timing requirements for PCIe, they split the monolithic PDI into two stages, stage 1 PDI and stage 2 PDI, where stage 1 PDI is loaded before the system is rebooted or it's loaded from flash. And it's small enough that only the bare minimum of the V80 is actually programmed so that it meets the PCIe timing constraints. And then when the system is fully booted up, stage 2 is programmed either via JTAG or PCIe. And because we have this flow working, the tandem document says that DFX is easy as just loading another bitstream through the same interface, and you can reconfigure the device that way. If you look further into the details, this method of delivering the stage 2 bitstreams seems easy enough, where using drivers such as QDMA or MCAP VSEC, all you need to do is write to that specific slave boot interface that's addressable via AXI with a specific PDI, and the device would automatically reconfigure the device. We went with QDMA because MCAP VSEC doesn't seem to be actively maintained at the moment, and we needed to downgrade our kernel to 5.4. But QDMA seems simple enough, and based on this knowledge, based on our understanding of the documentation and AEVD, we just implemented DFX on the basic AVD design, and using QDMA, we just wrote to the slave boot interface address to reconfigure the device with a new uh, user application. But then we quickly found out that if we did this, the whole system crashes. So we went back to the drawing board and tried to understand what was actually happening. And so we found out that because we couldn't do that with just DFX alone, maybe we theorized that tandem might be a factor in how the system is giving the how the FPGA is giving the host access to write to the slave boot interface. So we enabled tandem on the AVD design, and we just and everything just seemed to work fine. Vivado created two PDIs, and we could just program the V80 with it. But the problem arose where, when after programming the device with just the stage one PDI, when we rebooted the system, the actual V80 device was not visible to the host and not even visible in LSPCI. And based on the AVD documents, we found out that there's this logic block called the hardware discovery block that's responsible for enumerating the PCIe bars. And because Tandem only brings online the bare minimum, the hardware discovery block was not discoverable during the boot up phase of the machine, and thus the PCI device was not visible. And so this kind of showed that Tandem would not work because we didn't have the hardware discovery block. But then because we just wanted the FX to work, what we did next was we just because we needed the hardware discovery block to be visible to the host at boot, we just programmed both stage one and stage two before we did a soft reboot, and this seemed to work fairly well, where we were able to boot the system and actually see the AVD design as well. But then, similarly to the previous instance, when we wrote to the slave boot interface, this also crashed the system. At this point, we were kind of very baffled why this was happening. And we kind of theorized that maybe it's because controller 0 and controller 1 are not the same. And so we modified the AVD design to use controller 0 instead of controller 1. And initially, we just implemented tandem and tried to see what happened. To our surprise, what we saw was even without the hardware discovery block, with just the bare minimum Tandem 1 Stage 1, the system booted up fine and our device was visible to both the QDMA driver and to both LSPCI. And it was very simple to program Stage 2. All we had to do was write to the slave boot interface through the QDMA driver, and we were able to program the V80 with the second stage PDI and use it as it was supposed to. But then the problem was when we tried to implement DFX on top of the tandem implemented AEVD design, Vivado 24.2 gave us this error where it said tandem plus DFX bitstream generation is not supported for the V80. Thanks to our AMD colleagues in general, we were able to find out that tandem plus DFX for the V80 is currently gated in Vivado 24.2. But then after some internal discussions with Andrew and Mario and everyone else in the HACC team, we found out that this will be resolved in the upcoming release of 25.1. And we found out that this flow is working if you have the right tools. And for later on, when 25.1 comes out, people who want to implement DFX on V80, I think, should start with controller 0 and go through the tandem plus DFX flow to get this to work for their own designs. Just to wrap up, based on my experiments, this journey was quite tedious. It took hundreds of man hours, and it was a lot of trial and error, and just exploring the design space of tandem plus DFX. And based on my preliminary experiments, what we found out was CPM5 as CPM5 at least, for CPM5 on the V80 at least, controller 0 and controller 1 do not seem to be the same. And to deliver the stage 2 PDIs, we need to use controller 0. And based on based on open source data and internal discussions. For controller one, maybe upcoming features such as segmented configuration or SoC boot might fix this issue, but as is, tandem is the one that's actively supported at the moment. And so to get tandem to work, controller 0 is, I think, preferred at the moment, up until segmented configuration is fully supported for the V80s. And so right now, our current flow entails using tandem to deliver DFX over the DFX PDI and the stage 2 PDI using the QDMA driver. And this flow seems to fully work stably without any issue. And although it's not available to the public at the moment for 24.2, it should be available very soon with the release of 25.1. And there's a lot of trial and error for the V80s because it's so new that some of the documents hasn't been fully updated yet. So for users who are working with the V80s, what we recommend is, try everything and not fully trust the document to give you all the answers. With this, I think that's it for my presentation.
That's great. And we did have somebody who just popped in a question into the question and answer block here, and I'll encourage anybody else that may have questions to enter them in. The question here I can read for you if Gregory, if you don't see it, but they basically said in the first few slides, I see you emphasize the importance of programming via PCIe. Now for LVL accelerators, they should be also programmed via PCIe, and just asking some of the key differences, and just maybe if you would kind of reiterate a little bit of kind of what your PCIe programming experiences were and the needs there.
So are you talking about FPGAs in general? Like,
So I think it's for the LVL accelerators, particularly in this case. I mean, you had
so
kind of
the
alluded to the JTAG versus PCIe for the performance and speed at
mhm.
which, but if you had any other insights there.
So if you're talking about the other Alveo platforms like the U55C, the U280, because they've been out for a longer time, the flow is very stable. So all of the things I just said should just work if you just follow the documentation. And the Alveo platform is kind of, depends on how you view the Alveo platform. If you view the Alveo platform like the U55Cs as a Vivado platform, then you would do DFX over PCIe through the QDMA driver. But then if you view the U55C as a Vitis platform, then Vitis will manage everything for you, and you would never have to worry about this, as the Vitis platform would do DFX under the hood, and the user will never be aware of this. Does that answer your question, or?
Yeah, no, I think that helps clarify for hopefully and there was a follow-up talking about kind of partial bitstream programming in general, which this is again very specific to the LVO accelerators and
Hmm.
not just the general FPGA. So that's helpful. As we maybe allow a little bit of time for others if they did have other questions they wanted to enter in, and we'll have time towards the end also for general questions. I was hoping you may be able to just speak maybe briefly to sort of your next steps beyond the 2025.1 release, where this is, how does this fit more broadly into your research interests and efforts? If you want to speak just for a minute or two on that.
Okay, so um, the the V80 at least is very big. So and then we're looking into virtualization of the FPGA. And so previous works like Nimblock or Coyote have implemented this on previous generations of normal FPGAs that doesn't have the NOC. But now with this feature coming out and with this new hardware, we do want to explore how FPGAs fit into the new landscape of cloud-based computing. And so that's the goal for the research. We've only gone up to the point where we did a proof of concept of DFX. And so next steps will be to explore all the three key areas that we emphasized at the beginning of the presentation.